I guess I need to be louder. Can you hear me? Maybe you can't hear me. Uh-oh. Hello? I'm very quiet. Uh-oh. How about now? Is it better? How about now? Hello? Louder? Hello? Okay. All right, let's get started. We have one midterm in the books. One more to go. Okay. All right. What's going on? Okay. So assignments. So today's. I think everybody's demoed, if I'm not mistaken, or if you haven't demoed, make sure you get your projects submitted by tonight for Lab 3. And if you have demoed, you still need to submit your project, so get it in by tonight. Okay? So I get this question, I get panicked emails from people who demoed but didn't immediately submit their zip file. You have till the very last day to demo with 20% to get that zip file in, and that's today for Lab 3. Okay, well, your grade depends on when you demoed, not when you submit the file, but you have to submit the file. On Canvas, it's right there. Lab project submission closes, it was due the 30th when the demo was due, but you have until tonight to turn in the zip file. And Lab 4 is due this Thursday, the pre-lab tomorrow morning. Any questions? I had lots of questions. I had several questions about timing and the pre-lab and simulation. Okay, no questions. All right. If there are no questions, we shall forge ahead. Still no questions? Okay. I can't believe there's no question out there. It's hiding somewhere. Okay. Okay, so you've seen these two slides before, but they were at the end of lecture on Wednesday, and probably thinking more about the midterm at that point. So I want to go over these again because they are errors that I often see when people make state machines. Okay, so to have a state machine that is well-formed, it may not do what you want, but at least it is well-formed in the sense that it covers all the possibilities without conflict. Every state must have transitions that are mutually exclusive. So if you have a state and we have 3 variables, now there may be other variables that your state machine looks at, but they're not important in this state. So we don't even have to mention them because they're all don't cares in this state. But let's say in this state we need to pay attention A, B, and C. Then we have 3 arcs leaving state S, one of them coming back, with 3 different conditions. This arc is to be followed if A and B are both 0. This arc is to be followed if A is 0 and B is 1. So there's no conflict between the blue and the green. They can't both be true. But if we look at this arc, which has A or B, not C, there is a conflict. If A is false but B is true, both of these might be possible, right? Assuming C is 0 as well. And so if that particular input combination occurs, your logic is going to say, oh, I'm supposed to go to 2 states. And that's not good. In one hot, that means that two of your state bits will go high. If you're using some other state encoding, it probably means that you're going to go in a combination of two states, probably the OR of those two states. That's not good either. That may not even be any state that you've covered. Okay, so you have to make sure that all these arcs are mutually exclusive, and it's very easy to overlook this because you may have an arc for A going one place and an arc for B going another place, and then you don't think about, well, what if they're both true? What if A is true and B is true? What happens? Okay, so you should have one arc for A, and then the other arc should be for not A and B, and that makes them then mutually exclusive. Okay, so here we fix the problem by changing this arc so that it only holds when C is 1. Okay, so that's one important thing. The other thing is you shouldn't leave out a particular value that can occur. So in this case, our three arcs fail to tell the state what should happen if A is 1, B is 0, and C is 1. None of these expressions are true for this case. Now, if you're absolutely, positively, 100% sure that this input value will never occur, that it's not possible for A to be 1, B to be 0, and C to be 1, you're okay. But if that input value occurs, you haven't told it what state to go to. And in one hot, that generally means all your state bits go to 0. And then you are in no state at all. Okay, so you've got to make sure that you don't neglect a particular combination. Okay, so when you make your state machines in Lab 4 and Lab 5, make sure to pay attention to these two principles for every individual state. Have I covered all the possibilities? All right. Any questions on that? Okay, so today we are going to address that burning question that I'm sure has been keeping you awake at night. Should I make mealy or more machines when I design my circuits? And there are advantages to both. Sometimes you don't have a choice. The spec will tell you it needs to be mealy or that it needs to be more. Okay, but if you have a choice, you're designing your own system, generally you have the freedom to do one or the other. Okay, so we did these examples, I think, last Monday. We built an even block machine, and remember this machine looks for 2 1s. So if we start, or actually an even number of 1s. So if we start at chill, every time x is 1, we bounce back between these two states. And if we're in even state and x is 0, then we go to the eureka state and we output a 1. So we're looking for an even number of 1s followed by a 0. And the spec said the output should go high after you clock in the 0. So that means that we don't want to react right away. We want that 0 to change state, and then we want to be in a state where the output is 1. And it was only supposed to be 1 for 1 clock cycle. So we had to leave that state. There's no loop here. We always leave state eureka on the next clock edge. Okay. We then were asked to design a different version in which the output is supposed to react right away when x is 0. So instead of, when x is 0, and we're in state even, instead of changing state to a state that outputs 1, we are going to output 1 if x is 0. And that's why we have it on the arc here. If x is 1, we're not going to output a 0. We're going to go back to odd. Okay, so while we're in even, basically if x is 1, we're going to output 0, and if x is 0, we're going to output 1. And if x is going up and down while we're sitting here in even, the output's going to go up and down. It's going to react immediately. All right, and then we go back. Because I don't need a state where I have to output a 1, I can just go back to chill immediately. I don't need to have this extra state where I output a 1. Okay, and then we compared the output of the two. So y2 is the output of the second version, and y is the output of the first version. And one of the differences is when we get this 1 output. The even block, the Mealy version, the one where the output depends on the current input, can output the one clock cycle earlier, whereas the Moore version has to wait for it to change state, and then so you actually see that the output is 1 only when you actually were in Eureka and about to leave Eureka. Okay, so those are the two, and this is the simulation. In fact, if we were to run this in Vivado, it would look like this. And so one of the questions I know for the pre-lab, I asked you to simulate the message checker and supply the same inputs as a table in the text. And one of the questions I got was, wait a minute, how come the output is high? It's not supposed to be high according to the table. So if you look at the table in the text, it's only showing you the output values right at the clock edge. When you run the simulation, it's showing you the values of the outputs all the time. So if you look at y2 here, so we are in the even states here, right? We start in chill. Both machines start in chill. Then they go to odd when x is 1. And then when x is 1 again, they go to the even state. And now x is, let's see, we're in the even state. And here's x, and x is going low, and then high, and then low. So y2 is reacting. y2 goes high here. But this is between clock edges. So you wouldn't see this in the table, because the table's only showing you the values of y at the clock edge, right? When we looked at this, all right. When we looked at this table, we didn't see y2 going high until the 8th clock edge, right? And yet y2 is high here, but it's not high on a clock edge. Okay, but it is about to be high here. And so because that occurs right on a clock edge, you need to actually zoom in. And if you zoom in far enough, you'll see that here's the clock edge, and in fact, y2 was high and stayed high until after the clock edge. Okay? Okay, because if you're just looking at this view, you're going to wonder, gee, is y2 low or high here? Generally, it's going to be the value that it looks like before the clock edge, because nothing is changing near the clock edge. Yes?
For lab 4, would you say that either one of Moore or Mealy machines is a better idea than the other?
I think you're going to want states of both types, with outputs of both types. There are things that you don't want to do on ARCs. For example, if you remember our tap spike counter, where we incremented the counter. You don't want to do that on a loop. So you don't want to do that on a state that you're staying multiple cycles in, right? If you just wanted to increment the counter once after a bike, right? So that naturally should have been on a transition. Okay. If you need something to hold steady while you're in a state, then that can depend on a state. If you want, it is possible to have just a Moore machine, and I'm afraid most of you are going to not ever want to do a mealy before I'm done with lecture today. But it's kind of a waste to have extra states just so that your machine is Moore. But anyway, okay, all right. So I think somebody actually suggested this last time. If you have a mealy machine, can you just turn it into a Moore machine? And the answer is yes. How do you do that? You add a flip-flop to its output, right? Now I have a Moore machine because the output only depends on the state. Of course, now I have 3 flip-flops too, right? And I know I can do this with only 2 flip-flops, so this wasn't the best design. But yes, we could do that. This actually has a name. It's called a synchronized mealy machine. Okay, so that ends up being our basically this equivalent, though not as good a design as the original even blocks because of the number of flip-flops. Okay. All right, so what are some advantages or disadvantages of mealy versus Moore? Well, let's think about this. So here's our typical cloud circuit, our view of a state machine, right? We have our inputs. We have some combinational logic, which produces the next state. And this logic also, if it's a mealy machine, the inputs also go into the output logic. The output logic takes the state bits, the present state, and the inputs and generates the outputs. And so let's say you have a design with multiple mealy machines, and you're feeding the output of one mealy machine into the input of another. What you're doing is you're creating logic paths that are longer. You're adding them together. The delay gets added, right? We have to, in order for this to settle, we need this logic to settle, and we need this logic to settle. So we have the sum of the 2 delays of these output clouds. In a Moore machine, there is no path from an input to an output directly. The output only depends on these flip-flops. Right? So in terms of delay, well, delay, there's 3 components to it. There's a delay from the inputs to the next states. There's a delay from the present states of the first machine to the next states of the second machine. And also there's a delay from the present state of the second machine to the next state of the first machine and to the outputs. But now we're taking the maximum of the 2. They're not added together. So combining Moore machines doesn't create an additive delay. You don't end up needing to sum the delays of the 2 machines for your circuit to settle. So this is a very simple concept that you probably haven't. How many of you have taken 120? Okay, so what would you call breaking up a long combinational delay with flip-flops? Pipelining. Oh, did I put it on there? Oh, shoot. Oh. Ah. All right, I'm going to have to do it better. Okay. All right, so this is essentially pipelining, or, you think back to mid-century, what Ford did in the assembly line, where each stage can run in parallel, and so the whole thing's faster than if you built one car from beginning to end and then did each car like that. Okay, so this is an advantage of more, and I don't want to scare you. More Mealy machines are good. They have their place. I just want to preface this next problem. So some of you have already encountered this. And probably it was just a typo, but when we start combining machines, it can happen. So let's say you have one Mealy machine, and you feed its output into another Mealy machine. And then you take the output of the second Mealy machine and decide to feed it back into the first Mealy machine. It is possible that you have created a combinational loop. It is possible that this input drives this output, which drives this output, which comes back as this input. It doesn't go through any flip-flops. This is a combinational loop, and as you know, these can oscillate. And so it happens more often than you think. And when you take an output of your state machine, you might want to think, gee, is there something that I'm connecting to that's going to then affect my input immediately? And you have to be careful with that. So here's an example of what this is like and how you might encounter it. This is a really simple example. We have two finite state machines, two state machines. They each have two states. So they have one flip-flop, because only need one flip-flop for two states. Don't really need two flip-flops, even for one hot. Okay. So what happens here is that when H is high, the input is held high. And each of these flip-flops, if they're zero, they can interrupt the path, because what they can do is they can force these AND gates to be low. But if Q1 is high and Q2 is high, then these AND gates just pass the other wire through. And if H is low, this passes through. And we have one inverter here. So we have, when H is low and Q1 and Q2 are both high, we have an inverter in a loop. And as we know, that can go up and down. Okay, so this isn't going to be apparent to you necessarily. This is what it would look like on a schematic in Vivado, right? And let me show you what it would look like if you tried to implement this and simulate this. I used to do this live, running Vivado on my laptop, but it hosed my laptop so badly that I had to reboot, and it took too long, so instead I have a video of what happens. Okay, so here we are. The simulation is run to 1,000 nanoseconds, or 1 microsecond. We are taking steps of a half microsecond, and we are going to run the behavioral simulation. Notice that we were not able to generate a bit stream. We have an error. Okay. All right, let's go with the video then. Okay, somewhere my mouse is going. Is this not going? All right, one more click. Okay, here we go. Okay. All right, we're going to take a step here, half a microsecond. All right, we're at 1,500. Going to do another one, 2,000. Q1 and Q2 are low. Going to take one more step here. Here we go. We only made it to 2900. The simulation's running. It's not advancing. Time's not advancing. I've got the dreaded circle of death. Uh-oh, this is not good. Okay, the screen, okay. Okay, I got it back. So the way I got it back was I stopped it here, okay? If you see it running and nothing's happening, you might want to click that as soon as you can before it uses up all your memory and you have to reboot. Okay? If you have to reboot, it's no big deal. It'll come back. All right, so what happens? Well, the simulation is chasing that inverter loop. It's trying to figure out what the value is of that output. And when you're doing behavioral simulation, it has no information on delay. It just keeps plugging in values until the combinational logic settles. So it just, if it changes the input of a gate, if that changes the output, then it propagates that, and that changes the next gate, and it keeps chasing these gates going around, 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 and it will never advance time because it never settles. It always takes just 1 picosecond for your combinational logic to settle. This is, of course, not realistic, but it makes for much faster simulation because we just want to know if it's correct at this point. We don't care about the timing so much, and so we just quickly tell me if it's logically correct. That's what behavioral simulation does for it. And in an FPGA, with the speeds you're running at, that's enough. Okay, but in this case, it would never settled because it was chasing that loop. Okay, so let's see a different type of simulation. Yes?
I was just wondering if you could point out which loop in like the previous slide on the schematic, which loop it was like kind of chasing. I'm having trouble visualizing it.
This one.
Sorry, on the left or on the right? I can't see the mouse. Oh, sweet.
So the loop goes here, right? To activate this loop, though, we need H to be 0, right? Because if H is 1, then this is forced to 1, and it's not going to change. So we need H to be 0, we need Q1 to be 1, and we need Q2 to be 1. Okay, now these flip-flops will wake up with zeros. So they'll be fine until they both go to 1 and H goes low. When that happens, then the loop becomes activated, and it can go round and round and round. Okay, and I think you could see it here. I mean, you could follow it. Here's our input 8. This is our OR gate, so it goes here, goes here, goes here. Here's the AND gate, comes back around. All right, so that's the, what if we do a different kind of simulation? So we can also do what's called a timing simulation, where we use actual delays or delay estimates for our logic. And you can do this after you've implemented. You have to run the implementation first. And this is the simulation we get if we do that. Okay, so it's the same test bench. The only difference is I'm running the timing simulation. Okay. Here we go. All right, let's see if we can get past 2900 this time. Yay! Okay, we got past 2900. Oh, but there's something strange there. What's that? So let's zoom in there. Okay, there's the loop going up and down. But now the loop took time. It wasn't 0 time. It didn't have to wait for it to settle. Time still moved forward while it was trying to settle, and so we eventually got to the clock edge, and then time kept moving, okay? But as you can see, there's your combinational loop. Okay. All right, so what does this look like? What does the error look like? So this is the error you will get if you have a combinational loop. And you cannot get a bit file. Absolutely do not follow the directions here for how to get around it. We are not designing asynchronous circuits, and that's what you would get if you were. And this is not what you want. If you have a combinational loop, you have a mistake, and you need to fix it. And allowing combinational loops doesn't fix the mistake. Okay. What's most important here is the information on where it might be, which is in the last line. I don't know why they didn't put it in the first line, because that's really what you want. It's not always the best information, because it's the name of a net that starts the loop. For example, in our case, it might be H. That's not very helpful. Okay, so it's often difficult to find these things. If you're stuck, ask for help. Okay. Any questions on these? What?
I said we vibed, but that wasn't a very useful thing to say. Just, we're good.
You're good. Okay.
No question.
All right. Okay. So now we're going to talk about state minimization. Okay. So let's use a very simple state machine that you hopefully know about already, and that is the edge detector. Right? You all have one of these or many of these. You just need one version, but you can instantiate it several times. Right? This is purpose of the edge detector is to output Y, a high pulse for just one cycle whenever the input goes from low to high. So in order for Y to be high, we need Q1 to be low, and we need Q0 to be high. So we need a 0 followed by a 1. So this one detects a rising edge. If you want a falling edge, just move that bubble up here. So let's look at the state transition table of this little machine. It has 4 states. Usually you put Q1 and then Q0, but in this case I put it this way because Q0 is over here and Q1 is over here. It's less confusing, but be careful with the order here. Normally you want the more significant one first. Okay. All right, so basically this is pretty simple. Only in state 1, 0 will we output a 1. And basically you just shift in the new value. If x is 0, Q0 becomes 0, Q1 becomes Q0. If x is 1, Q0 becomes 1, and again Q1 becomes Q0. So basically it's a 2-bit shift register. That's all it is in an AND gate. Okay, so what does the state machine look like? It looks like this, right? We have 4 states. This is a Moore machine. The output only depends on the state. The output is only 1 in the state 1, 0. And we just bounce along between the states. One thing that you may have wondered, probably not, probably have to think about other things, is why are there 2 states that are really doing kind of the same thing? So if we look at the 2 states where Q0 is 0, we have a 0 here. We're not going to output a 1 until we actually clock in a 1, and Q0 is a 1, so nothing much is going to happen here. These 2 states are equivalent, right? They have the same output, and they go to the same next state, right? They both go to 0, 0 when x is 0, and they both go to 1, 0 when x is 1. So if I were to start the machine in state 0, 0 and run it forever, and then start the machine in state 0, 1 and feed it this exact same input, you'd never be able to tell what state I started in. They would, and the output would be exactly the same. So these states are redundant. They're equivalent. And so what we could do is say, well, I'm going to save a state. I'm going to zap the 0, 0 state. And now I need to, if any of my other states wanted to go to 0, 0, I need to change their mind and tell them to go to 0, 1 instead. And now I have one less state. If I'm doing one hot, I saved one flip-flop. If I'm doing a minimum length encoding, I didn't save anything because I still need 2 flip-flops. Okay. So this is one thing process that's done to synthesize minimal or efficient logic is to check for equivalent states or redundant states and remove them. This is also important to make a circuit testable, because if you have a lot of states that are equivalent, you can't tell which ones you're in. You can't tell which ones you tested. And it could be a problem if there's an error in one of them and you didn't detect it because you never tested that state. Okay, so let's talk about how we identify redundant states, because it's not all that simple. So let's go back to this slide. So here we were able to tell that the 2 states were the same because they had the same next state and they had the same output, right? So the rows look identical for these 2 states. But that isn't sufficient. It's possible for 2 states to be redundant even when their rows are not the same. And so here's an example of that. Let's say that I changed the edge detector. Remember, this used to go to itself, 0, 0. I change it now to go to 0, 1. This is still, these 2 states are still equivalent. You still can't distinguish between them because they were equivalent before, so going to 0, 0, going to 0, 1 didn't matter. They were the same. But now these 2 rows are different, right? These 2 rows are no longer identical, and yet these 2 states are the same. So how do we identify states that are the same? Well, we have an algorithm. That's a word you hear a lot these days. Okay, so 2 states are said to be distinguishable. We can tell 2 states apart if there is some input sequence that can cause them to produce different outputs. So if we have 2 versions of our machine and we start one machine in one state and another machine in another state, and then we feed them the same output, eventually they will produce a different output. Maybe not right away, maybe after only 26 inputs, but eventually there is some sequence of inputs that will force them to be different. Okay, if we can't do that, if we can never get them to be different, then we say they are indistinguishable and they are equivalent. Okay, and to figure out which states are equivalent, we use a very democratic algorithm called Moore's method. Basically, all states are assumed to be equivalent until proven otherwise. So that's the basic principle. All states are equivalent. So what's the first tip that 2 states are not equivalent? they have different output immediately. So we take our states and we divide them into groups where within each group they have a particular output value. Clearly, if one state outputs 1 and another state outputs 0, they're immediately not equivalent. We can distinguish between them. But this is the immediate output without feeding any input. All right. Then we go through an iterative process where for each group of states, we look at what group their next states are in. And we write down the group. Okay. And then after we've done that, we take each group and we look at the next states. If two states are going to the same next state groups, they stay together. Otherwise, we split up the group according to what their next groups are. Okay. And then if we split up any groups, then we have to repeat the process. But if we didn't split up any groups, if the groups remain the same after this process, then we're done. And we know that all the states within each group are equivalent. Okay, I know this is kind of vague, but so let's do an example. So here's our edge detector again. It has states A, B, and C. So our first step is a group states by output. So what are my groups here?
Your groups?
Yes. 0, okay, so those are two outputs, 0 and 1, but
A, B, and C.
is that what you're going to say? Yeah.
I know you got it.
Okay, so A, B, D, and C, right? A, B, D have the same output, and D and C has a different output. C outputs 1, A, B, and D output 0. I can't tell A, B, and D apart yet, but I can tell them apart from C. Okay, now we're doing step 2, and I'm looking at the next state groups. So A goes to B, which is in group 1 with a 0, and it goes to A, which is in group 1 with a 1. Okay, so the next group, the groups of the next states for A are 1 and 1. For B, it's D, which is in 1, but C, which is in 2. Right? With a 1, B will go to C. D will also go to group 1 with a 0 and group 2 with a 1. Okay? C goes to group 1 and group 1. Yeah, it goes to A and B, right, which are 1s. Okay, so that's step 2. Step 3, we have to split groups according to labels. So what are my groups now? Yes.
A,
Yeah.
then B and D, then C.
Let's see. Darn it, you didn't try to put A and C back together. Okay, so this is a very pessimistic in the sense that you never get back together. Once a group is separated, we cannot rejoin. So A and C cannot get back together. Right? And you know, that makes sense. A and C had this different outputs, so they were in different groups. It would not make sense for A and C to get back together. Right? And you may be tempted because their next states are the same, but don't be tempted. Okay, so we had a change here. So I have to go back to step 2. All right, and so I do this again. And now A goes, but now I have 3 groups, so they're labeled 1, 2, 3. It doesn't really matter what your labels are. You can use Greek letters, you can use symbols, you can use emojis, whatever you want. They just need to be labeled so you can identify the group. Okay, and this time A goes to 2. Let's see, A goes to B, which is in 2 now, and itself, which is in 1. B goes to D, which is in 2, and C, which is in 3. D goes to B, which is in 2, and C, which is in 3. And C goes to B, which is in 2, and A, which is in 1. And so my next groups are the same. Okay, so I had no change. And if I had no change, there's no point in doing this again. Because it's never going to change, right? And so I'm done. And those basically identified that B and D are equivalent, and A and C are different from A and B and each other. Yes?
So, is there any point to labeling the next state groups of A and C that second time around, since they're already alone?
Yeah, so you could save some time here, because once the state is by itself, you really don't need to know what group it's going to be in. It's always going to be by itself. Yes, so once the state's alone, you can just put whatever you want there. Okay, I did this so that somebody would try to put A and C back together, but it didn't work. All right, so let's do one for a Mealy machine. No, let's not do one? Yes? Okay. All right. So what are my first groups here? Anybody else? Yes. Yes. Okay. So they have to have the same output for the same input. So in this case, we could have had 4 possibilities here, but there was only 0, 1, and 0, 0. We don't have 1, 0, or 1, 1 here. And that's because I want to start out with big groups, otherwise it's over very soon. Okay, so we have 2 groups. And this is our first and next group. Okay, so you're basically just looking for the group of the next state, right? So ED, that's 1, 2. C is EB, that's 1, 2. Okay. It's very mechanical. Very easy to make a mistake. Okay, so after this A, C, E stay together, but now B and D separate from F. So F is by itself. Okay. And we do this again. And as pointed out, there's no point in doing F. Right? And we were almost done, except unfortunately for state E. It looked good. A and C are the same, but unfortunately E goes to F, which is state 3. So we have new groups. We're going to have to separate out E. So now I have AC, E is a separate B, D, and F. And I do this one more time. Hopefully there'll be no change. Okay. Now, if you want, you can actually put the name of the group here, and then when you're done, you can just use state 1 for group 1, state 2 for group 2, and state 3 for group 4, and then here you have the next states for right there written down. Okay. Or you can edit the transition table. So we need to get rid of 2 states. Which states shall we get rid of? C and D. Okay, in an academic environment, we obviously want to get rid of C and D. Okay, so let's get rid of D first. Goodbye. Okay, So you can cross out the row with D, but then wherever you have a D in the table, you need to put a B to replace it, right? Because D is no longer a state. And then we can get rid of C, right? Similarly, and there's our new state table. And it's only going to have 4 rows and 4 states. Okay? So we have gone from 6 states to 4 states, which means if I'm doing minimum length, I've gone from 3 flip-flops to 2 flip-flops. And if I'm doing K-maps, I've gone from 4 variable K-maps to 3 variable K-maps. Even bigger win. Okay. All right. Any questions on this? Yes?
Those dashes just mean they're the same as before.
These dashes? They're not the same as before. So what would these be? F goes to B and C, right? And B is 2, and okay, they happen to be the same. But it doesn't. What it means is I don't care. Because F is by itself, right? It's never going to rejoin a group. There's really no point in my figuring out what their next group is. And when you're doing this, maybe you start with 12 states. And each iteration, you get one more state. But as you get singletons, you can start to ignore them, right? Because you don't have to calculate their next state groups. Because it's not useful information. Okay. Any other questions?
This seems like the sort of thing grid paper would make really nice. This is what grid paper is.
Grid paper? Well, you make a lot of tables, and you're going to start drawing diagrams in your notebooks. No point in erasing diagrams, just draw a new one if it gets too messy. So, I still have 10 minutes. No questions.
Unless you want to give us some helpful hints on Lab 4 that I told several people to come to lecture for. I tried to taunt people into coming
I
to
see.
lecture. She'll give secret tips on Lab 4.
Secret tips. Start early.
Too late for that.
Okay.
I've already started.
Any questions on Lab 4? Everybody's got Lab 4 covered. You're all good.
I'm not all good. It's just that I may or may not have started like 2 hours before class, so I don't have good questions yet.
You don't have good questions. Yes?
I was looking at the state machine, and we may need to reset stuff.
Reset what? Reset what? So you have button R here connected to QSEC clocks. And basically when you hit button R, all of your flip-flops are zapped to 0, unless you said 1 instead. Okay? So button R should not go to anything but QSEC clocks. Don't put button R anywhere else. But
For one of the states, it's the loop where it's continuous. If you win,
yeah.
continuously flashing. So if you hit button R, it would still reset all the flip-flops.
You don't want it, but button R is like downloading again.
Okay.
You don't want to use button R. What do you want to reset?
When you win,
Yeah.
the LEDs are flashing,
Yeah.
and the digits are flashing.
Yeah.
Nothing else should work besides button R.
Yeah, so you don't have to put it in.
Right. So you're in a state with basically you don't leave.
Yeah. Until that resets.
And then button R is the only way out of that state. Yes. There's a hand over there. Did it? No?
I had that same question, whether or not that last state can just be a dead end.
It's a dead end. So it just loops. It has a loop with the condition 1, which means you always loop there. You're stuck until you hit. But that NAR is that NAR is just like, re-downloading. It's like pulling the plug on your computer, if you like, and plugging it back in. Yes. Go for over R. So your game counter needs to reset, right? Because what is it? It starts at 1F, right? So this isn't a reset to 0. It's kind of a restart, right? You have a counter, right? This counter has several different controls, one of which is load. Right, so this R input could be used to load a particular value. If you want to reset it to 0, you could also use the load for that. But in this case, I don't think you want to reset it to 0.
See, I did get a useful tip out of that.
Oh, okay. And any other? Yes.
When you start the board, is it mandatory that the game counter should be at 1F? Or is it okay for it to start at 0, 0? Because when I press button C, it'll go to 1F, but not when I turn on the board.
Well, are you showing it when you turn on the? Oh, yes, you are. What did I do?
Yeah, when your board's turned on, it'll just say 1F automatically.
It starts at 1F. You could do that. How do you get something to happen just once when you first wake up? In it?
Is there something else?
What's in it?
Oh, there's an optional parameter when you declare the flip-flops in Verilog. If you do hashtag init, and then
So you're going to make a counter that inits at 1F? Is that your idea? You're going to change your counter?
yeah, no, so that's why I didn't want to do that. That's why I was wondering.
So we talked about the fact that you could do that by loading 1F, right?
Yeah.
So you're going to want to do that as part of the game, and you're probably going to want to see what I'm writing.
Should we essentially make like a startup state?
So how do I generate a 1 for just one cycle right when the board wakes up?
Exactly.
How do I do that? Any ideas?
Flip-flop wrapped in inverter?
I want a flip-flop. Whoops, Q. That's going to be 1. And then it's immediately going to go to 0 after the first clock edge. So, gee, seems like I want to feed it a 0. But what if I do that? Okay. I can see the phones coming out. No. What if we do that? Do you think that will work? So on the first clock edge, this will be 1 to begin with when you reset. And then on the first clock edge, it'll go 0. And it'll never be 1 again until you hit button R.
For button C.
No, button C won't do it. Well, but presumably you have this coming. If you want it to, you can also cause this to happen other ways, right? Yes.
Could you explain then what exactly happens to logic before time 2000? Because I know that there's reasons we shouldn't have our simulations and such occur before
Okay.
time 2000.
So when you first wake up with your simulation, it's pretending to be the chip, and it's doing the download, and it's holding the flip-flops fixed at their initial value. and nothing will happen. Okay? So for the first 1,000, you won't have anything. After the first 1,000, I'm generating the clock for you, and I'm using the FPGA to generate the clock. I'm not giving you the 100 megahertz clock that comes in, and that clock takes some time to start up, which is why I want you to wait to 2,000.
Gotcha. But so I had assumed that something similar was happening on the physical board. I assume it's not then?
Well, yes, the download is happening. Yeah, my QSEC clock's in the chip too, right?
Gotcha. So having
Well, so it, nothing bad happens to your circuit while my clock's not running, right? It's just that the first clock edge doesn't actually occur till later. So if you're feeding it inputs, they're ignored.
But feeding an input of 0 forever, it's just gonna get ignored until the clock starts.
Right.
But then you've avoided the problem of having logic happening before the clock starts anyway, because the logic doesn't take.
Well, the problem is that if you're feeding it inputs and expecting it to react, it won't react because there's no clock.
But if it's just a force-driven input, then that's not a problem if
No.
the force-driven input is initialized before the clock starts, but it's forever the 0.
You can set it to 0. I just don't want you to start. I have this problem where people tell me, most things happening in simulation, and they just haven't run it long enough, right? If you were providing inputs and expected the outputs to react within that first 1,000, you're going to be very disappointed, and you're going to think something's wrong, but it's not. You just need to wait a little bit. Just wait 2 microseconds. A little patience. Okay. Have we used up all our time now? Yes. Okay. I'll see you Wednesday.